All right, let's dive in. Today, we are tackling a puzzle that'll make you rethink your next dinner party seating chart.
Ooh, this is a good one. A classic.
Imagine this. You've got several couples coming over, and you want to be a good host, keep things lively, right? So you decide to seat them around a table, men and women alternating. Sounds simple enough, but here's the catch. Absolutely no one can sit next to their own partner.
That's the problème de ménage, the ménage problem.
Exactly. And as you might guess, this seemingly straightforward seating arrangement quickly turns into, well, a mathematical puzzle. And a classic one at that.
Oh, absolutely.
Yeah.
A real brain teaser. And it pops up all over in mathematics.
Especially if you find yourself wandering through the OEIS, the online encyclopedia of integer sequences.
Which, let's be honest, if you're a number theory student, you probably are.
For sure. And today, we're zeroing in on a specific sequence, A000181. The title now, get ready for this, it's a bit of a mouthful. Coefficients of ménage hit polynomials.
A bit of a mouthful is right. But don't let that scare you off.
Because this sequence, it starts off innocently enough. 2, 15, 60, 4, 69, and so on. But trust me, folks, there are some fascinating combinatorial secrets hiding in these numbers. Secrets that are directly tied to our tricky seating arrangement.
What's really cool, though, is that this problem isn't new. It's not some recent invention.
Oh, yeah. It's got history.
It goes way back to 1891. Edward Lucas, you might recognize that name. He formally posed the ménage problem.
Ah, Lucas. Famous for quite a few things in math.
And get this, around the same time, Peter Guthrie Tate was also working on the problem, but from a completely different angle, not theory.
Wait, hold on. Knot theory? Like tying knots?
Yeah.
How in the world does that connect to figuring out where people sit at a dinner table?
It's all about constraints. In knot theory, you have these rules strands can cross, but they can't pass through each other. And just like that, the ménage problem is all about limitations. Who can be next to whom? So the math we use to count those arrangements, it's actually pretty similar. It's like a shared language for dealing with restrictions and what happens when you start counting the possibilities.
I see. So it's not just about knots and seating charts. It's about the math that connects them.
Exactly. It's the underlying structure.
Okay, so let's get back to the ménage problem itself. Now, we mentioned A000181, those ménage hit polynomials and their connection to seating couples. But when you look at the OEIS, there are actually several sequences related to this whole seating puzzle. How do they all fit together?
Right. So the most straightforward answer to the ménage problem, for a circular table at least, is found in sequence A059375. It just tells you the total number of valid seating arrangements for, let's say, n couples.
Okay, so that's for a circle. What if we're talking about a straight table?
Straight table, that's A00000222. Different shape, different sequence.
Makes sense. But then there's A000179, often called the ménage numbers. How does that one fit in?
Good point. A000179. It's like a close cousin, but it leaves out a little something. A factor of 2 times n factorial. That factor appears in the full count of arrangements, but A000179 strips it away.
So we've got all these different ménage sequences hanging around in the OEIS. What about those ménage hit polynomials and their coefficients? Our star of the show, A000181. Where do they come into the picture?
The ménage hit polynomials, they give us a whole new level of detail. They go beyond just counting the arrangements where no couples are sitting together. They take into account scenarios where some couples might be side by side.
So instead of just a pass or fail, we get a more detailed report.
Exactly. The coefficients in those polynomials, that's what makes up A000181. They tell us how many arrangements have 0 couples together, exactly 1 couple together, exactly 2, and so on. It's like getting a breakdown of all the possible failure scenarios, but in a good way.
It's like knowing not just whether you succeeded, but also how you might have failed.
Precisely. And that's where it gets really interesting, especially for those number theory students digging through the OEIS.
Because the entry for A000181, it points to some pretty wild mathematical properties. There's this complex linear recurrence relation conjectured by R.J. Mothar.
Right, that recurrence relation is a beast. It connects a term in the sequence to a bunch of previous terms, but the coefficients are themselves polynomials in n. It's a mouthful just to describe it.
But the fact that there is a structure like that that's saying something, it hints at some deeper order within the sequence itself.
Definitely. And finding and proving those kinds of recurrence relations, that's a big deal in the world of integer sequences. It's like finding a shortcut to understanding and generating those terms.
And the surprises keep coming. We've also got a conjecture by Mark van Hooge all about the divisibility of terms in the sequence by prime numbers greater than 3.
That's a good one. That conjecture, it claims a specific divisibility relationship involving a term an and terms further down the line, an plus p and an plus 2p, all tied together by a prime p bigger than 3.
And that kind of divisibility pattern, that's classic number theory, right? It suggests connections to things like modular arithmetic and deeper algebraic structures.
Absolutely. The fact that these combinatorial coefficients might follow such a rule, that's quite remarkable. It's like a hidden code waiting to be deciphered.
And the OEIS entry, it's a treasure map full of cross-references. We've got A005, A087 described as a diagonal, and links to A000179, the ménage numbers themselves, and A000045, another related sequence. What can we learn from these connections?
Think of those cross-references as breadcrumbs. The fact that A005087 is a diagonal, that suggests our A000181 might actually be part of the bigger picture. A two-dimensional array where the other rows and columns have their own combinatorial stories to tell, maybe variations or generalizations of the ménage problem.
And those links to A000179 and A000425.
They're reinforcing that close bond between the ménage hit polynomial coefficients and the core ménage numbers. Maybe they're just different ways of looking at the same structure or different tools to calculate and understand these numbers.
And if you really want to go down the rabbit hole, there's the list of adjacent sequences A000178, A00000178, and so on. They could be a goldmine of information.
Oh, for sure. Looking at those neighbors, you might spot patterns, differences in how they're generated, maybe even shared structures that you wouldn't see just looking at one sequence by itself. The OEIS is all about those connections, helping you see how different mathematical ideas weave together.
The description for A000181 even mentions a connection to the permanence of matrices with defects.
Yeah, that's getting into some more advanced territory, using tools from linear algebra. Basically, you can represent the constraints of the ménage problem, who can't sit next to whom, using a special kind of matrix. And then the permanent of that matrix, which is like a determinant, but without the alternating signs, it counts the number of valid seating arrangements. It's a neat example of how ideas from different areas of math can come together to solve combinatorial problems.
So to wrap it all up, our sequence of numbers 2, 15, 60, 469, and so on, they're the coefficients of those ménage hit polynomials, and they're much more than just a list.
Right, they're deeply embedded in this classic problem. They tell us about the final solution, but also about all those almost solutions where some couples might end up together.
And there are connections to knot theory, matrix theory, and some really interesting number-theoretic properties, like that recurrence relation and those divisibility rules.
It's a perfect example for number theory students exploring the OEIS. It shows how a seemingly simple puzzle can lead to a whole network of mathematical ideas with integer sequences that have deep and often still mysterious properties. It's a glimpse into the beauty and interconnectedness of math.
And that brings us to a final thought. How could those ménage hit polynomials themselves? Those polynomials whose coefficients make up A000181 give us even more insight into the nature of constrained permutations and the symmetries of the ménage problem. It's something to ponder as you keep exploring the amazing world of integer sequences. Thanks for joining us for this deep dive.